As I promised yesterday, no new stuff today, just going over all the theorems we did yesterday and applying them to both algebra and proofs, which are going to come back today in the statements reasons form. You'll see right here, right up above, I have some formulas that we may be able to use today in the law of sines and the law of cosines. We are going to be involving triangles today. And as you know, if it's not a right triangle, the only way I can find sides or angles is to either use law of sines or cosines. So please do not be shocked when we start using them here in a couple minutes. All right, here we go. Find the value of x to the nearest tenth, question number 1. Right off the bat, all right, x is a chord. And I see that part of the diameter is perpendicular to it, so I know it's getting bisected. So if there's any way I could find half of this chord here, I would be all set. All right, so we see C drawn to this point on the circle as a measure of 3 units. What is that called? All right, what is that segment called? All of us hopefully know it's the radius. And any other radius I draw in this circle from yesterday will also be a length of 3. So think about this right now. Is there any other radius I could draw in that will maybe help me find half of the chord so I can double it and find x? And hopefully many of you right now are drawing in this radius right here, which is 3. And similar to what we did yesterday, we can use Pythagorean theorem. And we can say 2 squared plus b squared, and the radius is acting as the hypotenuse, so I plug it in for c. Keep it going. B squared is equal to 5. And we're going to keep this in radical form, so that half the chord is the square root of 5. So if I wanted to find the full chord, I double it, so 2 times radical 5, but it does say, the directions do say, got to follow the directions. Directions do say nearest tenth, so I will go to my calculator right now, do 2 times the square root of 5, round that to the nearest tenth, and that's going to be 4.5. All right, so not a big deal on that one, nothing crazy. We just had to remember that any radii I draw in the circle will be 3. We also had the theorem that a diameter perpendicular to a chord bisects the chord. All right, now it's going to get a little bit crazier here in the next example. Just find chord x. All right, what's the length of chord x? Ooh, well, I don't have any diameter that's perpendicular to it, so it doesn't get bisected. I'm given 120 degrees for this arc measure and a radius of 12. All right, I want to start forming triangles here, so what we can do is we can draw in the other radius, which is also 12. All radii in a circle are congruent. And if we drew this triangle out, we got 12, 12. We're trying to find that side. Now, how can I use the 120? Go back to the second day of this unit. What type of angle is this angle right here, or this angle that I just drew out? That's a central angle. And how do I find all central angles? They're always equal to the arc measure. So if this arc is 120, this central angle is also 120. This is why I've given you the law of sines and cosines, all right? I only have one angle in this problem, so I cannot use law of sines, all right? Instead, I can use the law of cosines. Oh, I got it backwards, excuse me. Try that again. A squared equals b squared plus c squared minus 2bc cosine A. Let's review how to use this again. What you plug in for A is the side across from the angle in the problem, which is 120 for us. Side across is x. So x squared equals b and c, other two sides, 12 squared plus 12 squared minus 2 times 12 times 12 times the cosine of the angle in the problem, for us 120. Please make sure your calculator's in degree mode, because 120 degrees, all right, is not in radians, it's in degrees. So make sure your calculator's in degree mode. You can do this all in one step. Okay, you should be able to do this all in one step. And make sure this number is what x squared is equal to. So at the end, you do want to take the square root of it. And you want to round to the nearest tenth once again. I am getting 20.8. There's no units on here, so I won't put any on my answer. So 20.8 using the law of cosines. All right. All right. Next up, a lot tougher now. All right. I know this is question 3 for you guys. All right. Take a look at those directions because we're going to get serious here. Find the radius and the measure of arc AB. Oh boy. Okay, find the radius and the measure of arc AB. All right, well, let's take care of the radius first here in number 3. Again, we got a part of a diameter perpendicular to a chord, so we know it gets bisected. So we got 12 and 12. You want me to find the radius? Yeah, I'll find that radius because that forms a right triangle. So to find the radius, we can do 5 squared plus 12 squared equals the radius c squared. So we can go ahead and figure that one out pretty quickly, no big deal. So the radius is 13 feet. Nice job there. All right, now we have to actually find the measure of our, not the length, so I don't need any of those length formulas we talked about. I want to find the measure in degrees of this arc, okay? And if you remember how to find the measure of an arc, is equal to the central angle measure. All right, so if I drew in the other radius up here, I just found out that they're 13 feet long. Everybody see triangle ACB that I have created. Let me draw it out down here. You guys can draw it out as well. So I have, let me draw it a different way like it is on your paper. So I have A, B, C, and I just 13, 13, 24 at the beginning, and you're trying to find, if you can find this central angle right here, that is equal to your arc AB. All right, again, I only have one angle, can't use law of sine, so I'm going to use law of cosines once again. So again, what's the side opposite the angle I'm trying to find? 24, that's what I start off the law of cosines with, 24 squared equals 13 squared plus 13 squared minus 2 times 13 cosine x. Now I have to get the angle all by itself. All right, not too sure if we remember this or not, but now we got to go piece by piece. So 576, 13 squared plus 13 squared is 338. Minus 2 times 13 is also 338. Cosine x. I want to remind you guys, this is when I went nuts in class a couple units ago. You cannot combine these two. One has a variable, the other doesn't. You cannot combine them. So what we need to do is get this 138 over the other side by subtracting. So go ahead and subtract it to the other side. And we end up with 238 on the left. Negative, don't drop the negative sign. 338 cosine x on this side. Now we can divide both sides by negative 338. Negative 338. You can write out that long decimal as if you want. You can leave it as a fraction, which I think I'll do here. So the cosine of x, let's see what we end up with. 238 divided by negative 338. I have negative 119 over 169. All right, how do I get x again? Remember, anytime you want to find an angle, we go to the inverse button on your calculator. So x is going to be equal to the inverse of cosine negative 119 over 169. X, go right ahead and you can do that. And it asks to round to the nearest tenth. So X, the measure of arc AB, should be 134.8 degrees. All right. So the key here is find the central angle using law of sines or cosines, and then go ahead and you'll find the measure of the arc once you find the measure of the central angle. All right, here we go. If you guys want to stop the video, see if you can do this on your own. I'll put up the work. So if you want to stop it right now, go ahead and try to get the radius. Again, it's being bisected because this part of the diameter is perpendicular to a chord. All right, so here's what you have right now. You got your right triangle. You got 6, and that breaks it up into 3 here. And what's my hypotenuse length right there? So Pythagorean theorem. Come on, you're better than that. We got 45 equals c squared. And yes, we are going to leave it. Actually, we don't need to leave it in simplest radical form because it does say nearest tenth for the directions. So our radius length is 6.7. All right. Whew, looking good. All right, now let's find that central angle. So if I draw my triangle out real quick, I'm going to have 6.7, 6.7, 6 on the bottom. And again, once I find that central angle, it'll be equal to arc AB. So you guys can go ahead right now, do law of cosines just like we did in the previous problem. Go ahead, stop the video. Just don't keep watching and write down the final answer. You should get 53.1 degrees as your final answer there. Again, try out the work, please. You're not going to know how to do it just following me. All right, got to try it on your own. 53.1. All right. All right. Wish I was here to celebrate with you guys the return of our buddies, the proofs. But now we're going to be using some circle facts and old ones too. You know, reflexive, addition, subtraction, substitution, all coming back now. Last unit of proof, so enjoy it while you can. You'll see our job on this proof is to prove BOC congruent to AOC. Real quickly, there were 5 ways to prove triangles congruent. And the one everyone forgets about, HL. All right, let's see what we're given here. We're given arc AC and arc CB are congruent. So the arcs are congruent. So I need to start getting sides and angles congruent in both those triangles. Well, let's use something old before we get into the circle theorems, and that is OC is congruent to itself. Have to enjoy that. All right, and then I noticed, now let's get to some circle facts. OA and OB have to be congruent because they're what in the circle? What do we call OA? What do we call that segment OB? Those are radii. And we found out yesterday that in a circle, all radii are congruent. Okay. So 2 pairs of sides. All right, we could go a couple different ways from here. We could say because the arcs are congruent, so are the central angles. Or this is the way I'm going to, since the arcs are congruent, so are chords AC congruent to CB. And if you remember the theorem, think about it. What was I given? I was given congruent arcs. And I said that they imply congruent chord. That's how you know the order. Whatever was given to you should come first. And then if you take a look, that should be enough to say the triangles are congruent. Not too bad. Triangle BOC congruent to triangle AOC. by the method of side, side, side. Okay, again, if you chose to do the central angles instead, your method would have been side, angle, side. And one more proof before I let you go on your own. Uses another of the circle facts we learned yesterday. All right, now I need to prove, take a look, a little bit different now. CFW congruent to CEW. Well, the only way I'm going to do that is if I prove a pair of triangles congruent. Okay, so there's only two triangles in there, so let's get those two triangles congruent before we do anything. So I have radius OC perpendicular to chord EF. Okay, so how can I get those triangles? So let's go over some old stuff first before we bring in the new circle theorems. Right off the bat, we can say WC is not WE. I have WC congruent to WC, reflexive. And yes, I know it's been a while. Kick the rust off, but we can say the right angles are congruent. But first we need to say that angle EWC and angle CWF are right angles. And if you remember our reason, perpendicular lines form right angles. And then right next step, now you can say they're congruent. And reason, all right angles are congruent. Whew. All right, so I need one more pair of sides or angles, and here's where it comes, that radius is perpendicular to a chord. And if you remember yesterday, if I have a part of a diameter, in this case a radius that's perpendicular to a chord, the chord gets bisected, all right, which would mean WE is congruent to WF. But I cannot write that, this next step. All right, the theorem doesn't say the two little pieces are equal. The theorem says the following, that if it's perpendicular, that OC bisects the chord EF. That's what the theorem says. The theorem does not say the tiny little two pieces are congruent. This was the long one from yesterday. So diameter, or you can write radius if you want, diameter perpendicular to a chord bisects the chord. Then in step 6, you can say, oh, because it's bisecting, now the two pieces, EF or EW, is congruent to WF. That's definition of a bisector. Now you have enough pieces to say the triangles are congruent. Just make sure they're in the correct order. So triangle WFC is congruent to triangle WEC by side, angle, side. And then final step, let it roll off the tongue. It's just like riding a bike. Get up and go again. CFW is congruent to angle CEW. Let it roll. CPCTC. Okay, the proofs in the packet tonight are very, very similar to this one. I will let you know there's a mistake on Aspen on one of the proofs. I want to see if any of you can catch it and let me know on Monday. All right, so get to it. Start the either the homework from last night or the assignment tonight. Both will be checked Monday.